Next, we have a keynote speech from our friend, at Douai, and talking about the last development. Yesterday, Karine Lefebvre, over there from Zatico, made a long presentation, not long, nice and good presentation about the properties of several kiln clays that have been calcined with different techniques, flash calciner, microwave, and so on. And Professor is going to explain where it comes from and what's the source of it. And you see it's a complete virtuous circle of the system. It's beautiful. Thank you.
Thank you, Ralph. Je vais garder le temps quand même. 21. Hop, super. Hi everybody. Thank you for having me. It's each year the same feeling. Great pleasure meeting you, meeting all of you, and having these great discussions. So for my today's presentation, I'm going to talk about this project we have started back to January. This is an Interact project with the team leader in here, the Ceramic Research Center, the Belgium Ceramic Research Center, and all the partners that are on this slide. So let me just describe very briefly the aiming of this project. So this project is an Interact project, as I said earlier, targeting to strengthen the resilience to climate change and also the adaptation. And the idea we had here is to use geopolymeric material as a very solid candidate to develop durable and environmental friendly materials. So we have also decided to use in this project a large spectra of materials, raw material and reused material, to adapt it to geopolymeric binders and elements. So since as we just started the project, we are focusing on. Oh, I have these slides that are not appearing properly. Sorry, I don't know why they don't appear properly. J'ai deux slides qui se cachent, pas pourquoi.
Here. Oh, should we see the
Okay, we get it.
It's a little bit
Okay,
tiny.
thank you. So at the end of this project, we'll be able to build a mapping in this north part of Europe that will identify the raw and the recycled resources that could be adapted to geopolymeric industry, and also we'll build up recipes and demonstrators that will show people that okay, geopolymer material are okay to develop material for any kind of use. And also, we are having work on standardization, and I think it's an important point to validate the large use of geopolymer. And also, we are having formation workshops and research paper that will be published at the end of the project, and make solid connection between academics and industrial all around geopolymer. So these are the partners included in the project. So the team leader, the CRIBC from Belgium, and also all these partners around between France and Belgium. And in our part, we will be participating in characterization, in the characterization and the improvement of raw material. I mean by that the thermal activation by flash calcination. So all the materials that will be used as precursors in the project will be prepared and flash calcined in our laboratory at Douai. And also we'll be participating in concrete formulation and also in studies in the early age and long-term behaviors of the concrete, the geopolymer concrete that will be developed in the project. So our starting point is our clays. So clays are, as you maybe know it, very interesting, very particular materials with specific properties. Notably their fineness, and also you have to know they are composed by hydrated phyllosilicates, so that are what we are going to activate through our process. So by activate, I mean here thermal activation, flash calcination. So these materials have specific properties like their plasticity, their high specific surface area that plays a major role in their reactivity and water retention, for example. And also they are used in a large spectra of application in construction industry, regular cement, cementitious material, bricks, concrete, etc. And here we are adapting them largely in geopolymers. We have some limitation, technical limitation that we are, let's say, challenges. For example, some clays that need more energy, more thermal energy to be activated. They are also included in the project. And we are using also different kind of activation techniques. As we know that at the end of the process, the activation techniques we are applying will be able to boost the reactivity of the products. Up. So here you have a description of the large techniques that are routes that are mainly used to activate clays or, let's say, minerals in general. We have the classic thermal activation. We mean by that the regular furnace we use, or rotary kiln that can be used to activate clays, but they need times and more energy to be efficient. So the heating temperature could be between 600 degrees C to 900 degrees C, depending on the type of clays. The second one, which is our option, our beloved option, which is the flash calcination. As we have the chance to have a flash calciner in our lab, this principle is very efficient, very quick. It's efficient in less than 1 second, and it does not need so much energy to reach these figures, and it's not so complex. These are the main advantages that we see in flash calcination, and that's why we prefer using it in this project instead of the others. However, we are going to combine it, for example, with the mechanical activation. We need to prepare the material before we flash calcine. We can't calcine any kind of material. They need to be dry. They need to be very fine. So drying and pushing it to very fine material, we are applying kind of mechanical activation or mechanosynthesis. We are also using it to have very fine, so the thumb rule here is the finer the better in our situation. So we are pushing very fine, and we'll see some figures and some results we already have. And combining these two principles, we will be able to be totally efficient when activation comes on. So here a few description of the materials and the techniques we use. We have different kind of milling processes. So cyclone mill or flail mill or ball mill, depending on the type of material we have, depending on the complexity, depending on the outcome needed, we prefer one to another one. So in this project, we will be starting by flail mill. We have it available in our lab, and we can produce, let's say, something like 50 kilograms per day, which is enough in our situation at this level of the project. And we will push it to something different if needed. And here we can see few examples of clays that was flash calcined. So the change in color, which is not the only change we have. We have also a chemical change in terms of reactivity. and physical change also in terms of shape. So we can see here in this map, in this SEM, this is on a sediment particle that was identified by SEM, in which this specific round shape, which is very interesting because it is going to play a roller effect, having a roller effect when it's used in a matrix. It also will be able to trigger the reactivity of the overall process, as it serves as a nucleation point. So this is not something that occurs all the time. Notably with clays, we don't identify this type of formation. But remember, in this project, we are open. We are using clays, we are using sediment, we are using raw or reused material. We are very large. Let's say anything that contains alumina and silica. Let's say it that way. So for those who are not familiar with flash calcination, so this is the principle of flash calcination. So this process starts right here with the feeder. So in this feeder we put the ready material, the dry and fine particles that will come up to the calcination chamber, which is here. So in this calcination chamber we have the zoom here, and you see it here in the photo. In this calcination chamber we have the flame and we have the right temperature. So in general between 600 to, at the topmost, 850 for the one we have. And then the material comes into the calcination chamber at this point, and very quickly they are going to drop down due to the gravity, and they will be first cooled down. So we will be moving from 600, 750 degrees C to 100 degrees C very quickly in the matter of seconds. And this will trigger the reactivity after the dehydroxylation, because when they come into the calcination chamber, we have the dehydroxylation, so the OH group are going to be eliminated, and the site will become very super reactive. Then we collect the material up to the cyclone and up to the filters. So 95% of the material will be collected under the cyclone, and the rest under the filters. And the material will be right after ready to be used. No post-processing. So this is very interesting that we don't always have in traditional calcination. So quick process, we're making something like 10 to 20 kilograms per hour with this process, low energy and cost effective, no post-processing. When polluants are present, they can be largely eliminated after the process. It's adaptable to a large spectra of material, soil, excavated soils, clay, sediment, any kind of mineral, let's say any kind of minerals, depending on the one. So it's now important to target the right temperature, the right calcination temperature. How do we decide it? In general, we use the TGA, so thermogravimetric analysis, to identify the right temperature. So with the thermogravimetric analysis, we know where the dehydration occurs, in general between 100 degrees C to 250 degrees C. Then the dehydroxylation that will occur between 400 degrees C to 900 degrees C, depending on the minerals. And after that, we have the recrystallization, what we don't want. So we are going to stay in this spot, depending on the clay. In kaolinitic clay, the window we have is quite large. In illitic clay, it's narrower, and in monomorphic clays, it's super narrow. So depending on the clay you have, that's why it's important, and it was Professor Davidovich reminded us, it's important to know the mineralogy of your material before you start anything. So once the flash calcination is applied, the material will be now ready to be used in geopolymeric application or any other type of application or use. So here, for this project, we already started the characterization with our Belgium colleagues that already prepared the material and bring it to us, and we will do additional investigation and then proceed to the calcination. So the calcination is already done with Youssef. And so the material at the beginning needs to be dried, then prepared. So meaning by that the grinding process to have something very fine. So you can see here the particle size distribution for 3 clays, for 5 materials we are starting with, but we are at this time focusing on the 3 first material. So the white kaolin, the yellow one, and the red one. And you can see here they are very fine. So less than the D90 is less than 40 microns, and the D10 is something like 1 micron. So very fine. So this guarantees us, okay, the flash calcination is going to be efficient. So this is an important point. So we have now collected this material. We did the TGA. We know the right spot for the calcination, and we did the calcination last week, I think. So here are the first trials our Belgium colleagues also did to identify the reactivity, to investigate the reactivity of the material. So here we have the tests that were done on this material. So these one were calcined traditionally. These are the first investigation, and they were calcined traditionally, and then we performed the test to identify the reactivity. And we can see, okay, these materials that were calcined at around 700 degrees C to 750 degrees C, 750 degrees C, they were reactive because they develop heat when they are mixed with silicate, I mean in a geopolymeric binder. So in another studies we are also doing in this project with our colleague from Ghent University, we're developing mortars, and we are going to make concretes also. And the idea of this study was to investigate few things. So we have investigated the compatibility between the reagent and the precursors. So to do that, we have selected different commercial precursors, metakaolins, and we have selected different source of reagents. And we were interested in seeing, okay, how these are compatible, how they are going to behave in terms of fresh state behavior, in terms of hardened state behavior. And we have seen different things, doing a lot of investigation using different techniques, investigating the porosity with the MIP, the chemistry with the FTR, to assess if we are truly making geopolymer material using the NMR. We are able, okay, to see, okay, we are making geopolymers. Some reagent should not be compatible with some precursors. So that's something I think you need to investigate and be sure, okay, you are not just mixing material randomly. Also, we have seen how they behave when we cure it underwater, and we have some surprise, as we have seen that, okay, when we mix a particular type of reagent and a particular type of precursors, they just have a weird behavior when they are when they are cured in the water, because some of them, they cracked inside the water, and we were able to hear the cracking. So once they are inside the water, we have internal stress, then they break like nothing. So once again investigating the porosity, the compatibility is something important. Also the cracking that needs to be controlled is something important regarding the chemistry, regarding the composition. We were able to see also here. We were able also to see here that okay, workability is truly controlled by the type of reagent that are used. We have seen that potassium-based is very good to have good workability. Sodium is less good. However, sodium could be very good for long-term properties. We have seen that also. So the best what I mean by that is the best option could be maybe what Alex and the others have seen is to create something hybrid. So we take benefit from potassium-based material and we take benefit from sodium-based material. And that will be maybe the lesson we have learned from this study. Also, we have a few investigations, and here the graph is just out. I don't know why, but we should have graphs here. Maybe I can share it with the PDF. I don't know why.
Keep secret.
Yeah, they get it erased. I don't know why, but we should have the NMR graphs here. I don't know if I can open the PDF file. Sorry for that.
Here, and you are here.
Why? Exactly.
This one.
Yes.
Okay, please.
Yeah, thank you. Up. I need to move it.
Yeah, you need to move it to the other side.
Yes.
Let's
Yeah,
do
again.
it this way.
Thank you. So here you can see the NMR.
You have a laser.
Okay, thank you. You can see here the NMR graphs. So we have few things here. At the bottom here, we have the commercial metakaolin. Some of the commercial metakaolin that have been used in this formulation. So the GeoFlash S, well-known GeoFlash S, and the M88 also. We see here in this material we identify what we need to identify, which is the aluminum 5 and the aluminum 4 coordination that mainly control the reactivity. So they are here. And also for these graphs, these are the NMR on the paste and mortars that were made from these precursors. So in these mortars, we see here, okay, we have the Q4 coordination. What is Q3 and Q4 coordination, what we need in geopolymeric material. And if you don't have this installation available, I mean, if you don't have access to the NMR, you know, maybe you already know it, using the water boiling test will tell you, okay, you have a geopolymeric material or not. Faut bouger ici, hein. Il reste une ou deux.
Oui. Non, non.
On va y arriver.
Ça va marcher. Ah. Hop. Hop.
Thank you. So now for the next stages of the project. Since January, we're making material processing, so to be able to do the flash calcination. So the flash calcination is now done. We are moving to the post characterization and the formulation of mortars and concrete later. So we're also making ordinary concrete application, but also fire resistant application. Also, we are targeting something very large. And we think by that, okay, industrials can see benefit from moving to geopolymers and effectively move to there. And that's what we need to push things very far from what we are right now. And so the flash calcination and conventional calcination are now done. And for the next period, we are going to move to the demonstrators also for next year. And we will also investigate the LCA, which is important, and the mapping that I talked about in the beginning. And yeah, for now we are just focusing on preparing the material and share it with all the partners to move to next steps. So before I finish, 2 slides. I was able to publish these 2 books here this year, and for this one. Fortunately or unfortunately, it's in French. I'm sorry for that. But what I would like to point out here is I put it's not a chapter, but a section on geopolymeric material. And I think it's important to make graduate students familiar with geopolymeric material. So that's how this book was designed, to make them familiar with this material, and maybe when later they will be professional, they will adopt it and maybe develop it more. And the second one is just for material mechanics, a little bit far from the current subject. I think that's it for me. Thank you for listening.
Thank you very much, Professor Amart, for this exhaustive presentation on how to transform a potential waste dirt earth into a very reactive potential precursor for geopolymer, a cloche, not only cement but also several things. And you see that he has followed all the steps that we are teaching.
Yeah.
And in the end, the results are pretty good because he understands all the steps, all the things, and yeah. Oh, sorry, I need to drink some. Please.
Yeah, hello.
Hello. Hi.
Again. Thank you for the presentation. Really
Welcome.
Nice. One question. Something I came across in the Netherlands a lot the last year and years before also. This you call it a myth, but I'm not sure if it's a myth. But it's what regular concrete producers tell me constantly, starting to talk about geopolymer. It's the metakaolin. Since it's also burned, you have a very high footprint of that. So your LCA values will become really bad the moment you start to use metakaolin. And yeah, of course, I don't agree with that. But this is the thing what the traditional concrete industry constantly tells me when I start talking about LCAs and low footprints of geopolymer in comparison to regular concrete. So it is very important that you get some sort of LCA.
Exactly.
Because this really, especially this flash calcination, it's very important that you show the traditional concrete industry the lower CO2 footprint of this stuff. Because this is what moves people nowadays. I noticed with the biochar thing, you get a lot of movement in the concrete industry when you start to talk about reduced footprint. And I think it's a topic we are not addressing enough in this course, because this is what makes the concrete industry move right now, at least in the Netherlands.
I do believe that totally, and with Geoffroy and all the team, I think we are in the same philosophy. I do think that calcined clay are not a problem at all. As cementitious industry, they are now convinced that okay, calcined clay is a very good option, and we're just telling them okay, you can use also calcined clay to make a very different material, but also durable and cost-effective, which are geopolymers.
One thing to add is that we did an LCA in our company. We had a whole department doing this type of thing. And we took a stab at it first in our department, and the biggest problem that we had was understanding what the footprint of concrete is. Because depending on how strong the concrete is it a special purpose, it can vary by an order of magnitude.
Yeah,
right?
absolutely.
And so finding your target, what are you comparing to, is hugely important. And then the other part of it is that a lot of these things are coming out, and if you look at the papers over time, their footprint is going down. I don't know if it's because they're making improvements or if that's just because that's what they're trying to show. Right? And so that was the hardest problem that we had. And even we just kind of picked the middle of the road, and we ended up with a 90% reduction in footprint. Going to geopolymer is the way we're formulating it. So it's there, but that's the biggest challenge of what are you actually comparing to.
Yeah, sure. Sure.
Yeah, and also they're cutting up the cement.
Yeah.
Cutting up the cement with metakaolin.
Exactly.
To reduce the footprint.
The LC3 cement, yeah.
Is
Doesn't